This is Mech 383, Kinematics and Dynamics. Here we have Project 4 and its physical representation. We're going to start with forward kinematics by pressing 1. In comes a photo representation of the system to reference your inputs off of. So we're going to go with 45 degrees for the first one, 92, 40, 52 for the second one, for the L1, which translates to these. Then we're going to do A2, 45, and then we're going to do 92, 40, 52. And that's going to be, so these are our lengths, which is the stick length in millimeters. And that's just the distance between center to center of these holes inside of the popsicle sticks. So that's what we're going to use for our lengths. They're all going to be the same because all the popsicle sticks are cut to the same. So we have that there. And then it's going to give us inches in millimeter value. So we're looking more at these millimeter values, but we could use the inches too. But we're gonna come over here and we're gonna take the first motor and turn it to 45. So that's about 45 right there if you lay it down. So, just a little bit more. And then we're gonna take this guy, move him to 45 as well. Okay, so those both looking 45, 45. Here's the system. We're gonna just lift them up, make a quick dot. So we got a dot right where he was. So put him back there. See, boom, boom, 45, 45. Then we're going to measure. So we'll take him, calipers real quick, and take a quick measurement of the distance between the x-axis and that spot on it. All right, I lost you there, but we're just gonna keep going real quick. So still making the same measurement that we were before. Swear I haven't moved nothing. But that is looking like maybe a little too far there, but hold on. That's looking about 41 actually. So 4.1, 41 inches for X. And then for Y, we're going to take the ruler in that same spot. It's looking about 5 7/8. Maybe a little less. Maybe a little less. 5 and 13/16. Okay, let's write that down. 5. See, is that 5? Yep, 5 and 13/16 inches. So let's convert those real quick. You can already see we're pretty close though with those two, 4.1, 5 and 13/16. So I'll show you the millimeters though real quick. So 4.141. That's 105. And we have 111 down here, so a couple off, but not too many. Then we'll look at the other one, which was 5 and 13, 16. And that's 147, which is just 2 off as well. So pretty close there, pretty close. So it's asking to go again. So we'll click go again and we'll show you inverse. Sorry, my phone keeps running out of storage, but here's inverse kinematics. So we selected 2, went into inverse kinematics, and it's asking for an XY coordinate. So I like to plot this usually, because I like to first create a mock angle so it can be cross-referenced back. So we're just going to do something like 90, 45. Something I can do very easily. And then we're just going to make a spot. So we got 90 there, 45 there, make a spot. Chem. Then we're going to measure X and Y, so X. Because it should come back as the same angles that we give it right here. So if we take this spot right here, measure it out. Sorry, I'm not the best cameraman, but okay. We got 3, 2, 4, 1 inches. So we got that guy. And then we'll look at him from the Y. And we got him out of the way. I'm going to take the ruler, run him for the Y. I'd use the calipers, but they're just not long enough. So, let's see if I can get it right next to you. It's about 5. Maybe 5 and a 16. We're gonna go with 5 just to be safe, yeah. Let's go 5 inches. There we go, 5 inches. We can also check at 5 and 16th, but kind of the cool part about the tool. You can always go to both. So that's gonna be 127 millimeters and 324 inches. I mean 3.241 inches is 82.3214. Okay. So this is our X and that is our Y. So we're going to take our X and put it in. Which is 82.3214. Then our Y is 127. Then we're gonna use the same lengths as the sticks that we're actually using because it's kind of a requirement to get the most accurate results we can get right now. And then, as you can see, it's once again very, very close. 92 and 48. The angle of servo 1 was in fact at 90. If we go back to that. And then angle 1 was at 45. And then, yeah, so it gave a pretty close result. I think some of that was because just the size of the thickness of the wood and the ruler and the calipers. Just these are pretty close actually. This gives a pretty close result. But yeah, so that's forward and reverse or inverse kinematics for this guy. Thank you for watching. So the code that was involved with this project, we first import the numpy library as np, and then we're going to use the polling active equals true to start our loop. And then we have our two drawings here, which are just functions that I can call when we need like to bring the drawings into the project. I have them called a couple times here. Twice for the two different drawings. And then we have our first function that's calculating. This is going to be our forward kinematics. And then I just run through the math formulas, turning things to radians, taking them and assigning them back. And I just keep running through the math formulas, use some square roots and arctangent, arccosine, cosine sine. And then we take these values and we put them together and we get our x and y, and then we return our x and y. Then we call that function later on down here. We'll come back to that. I'll show you where I call that later on. Same thing for the inverse, except we're going to take the x and y in instead of our theta, L1, theta b, L2, and d. So this time we're taking x, y, L1, L2, and d, because that's what's required for these formulas. We turn them all into floats up here. We also turn them into floats down here, but just to make sure. Then we just take the 180 minus the E2 and B1 degrees. And we get our final degrees. So this should be our angle of servo 1, angle of servo 2. And then we go to our loop, which is going to be asking all of our information. Would you like to use forward, inverse, kinematics, all of our print statements? And then you can choose one or two, and that'll give you forward or inverse. I added in a bounds, and that's the distance between the two angles can only be a certain amount. Otherwise, it's outside of the system's bounds. So I added that. I found that it was 63. You add your lengths 1, lengths 2 here, your theta A, theta B, your distance from arm 1 to arm 2, and then I call the first function here, calculate coordinates and assign it to x, y, and then I present the x and y. And then choice 2, we call drawing 2 for the inverse functions. We take in the x and y, we take our x and assign it to x, we take our y and assign it to y, our L1 and assign it to L1, L2, and our distance between. And then I call the inverse coordinates function, which is going to return x, y, L1, L2, LD. And what we're really looking for is the f degrees and the g final. And then we're going to print the angle of servo 1 and then the angle of servo 2. And then we just restart the program if necessary. So that is pretty much the code for project 4. That is everything. Yeah, these are just ASCII text generated. Just something to show visual representation. But yep, that is everything for this project 4. Thank you for watching.